Alright, let's talk about some more rings. So let's say some things about ideals. So if we have two ideals, fancy A and fancy B, um, then we can consider their sum. And this will be the collection of all things of the form A plus B, where A is taken from A and B is taken from B. And if we think of A times B, now, how we define this is that we don't just take things of the form A times B, where A is in A and B is in B. We want this to be an ideal. We're going to prove that, or we're going to see that these sets are ideals. And ideals have to be closed under addition. So in order to make this closed under addition, you need to consider finite sums of things of this form. So you take something in A times something in B, and consider finite sums of these things. So n could be, this should be an n here, but just any finite natural number. So clearly these things are going to be subgroups because, so your A is a subgroup of R, B is a subgroup of R, so they'll be subgroups. So yeah, just looking at plus, A is a subgroup of R, so, and B is a subgroup of R. You take any things of this form, then because addition is commutative, you can move the A's together and the B's together. And then if you multiply something in A, if you multiply together, or if you take any element in the ring and multiply it by an element in here, then you distribute it through and use the fact that these are both ideals, and prove that what you get out is something that's something in A plus something in B. And here the argument is really similar, but you use that, you've got, let's see here, what's going to happen here? I think that, like, well, for these things, you do have to consider multiplication on the left and on the right. So here, multiplication on the left and on the right, they'll both work by distributivity because we have distributivity on both sides. Here, when we distribute, if you take like an element R and multiply it by a sum like this, then if you multiply the R on the left, then you'll get the sums of the R times AI times BI. So you can basically bring the R inside every single term here. But if you multiply on the right, the R comes here. So when you distribute it through, it'll be AI times BI times R. And then this R times AI, that will be in A because A is an ideal, and BI times R, that will be in B because B is an ideal. So that's how we get that this is going to be an ideal. All right. So we talked last time, or in one of the previous videos, about how if you take two ideals and consider their intersection, you get an ideal as well. It turns out that if you take any collection of ideals, then their intersection is an ideal. This could even be like a countable, like intersecting a whole like countable collection of ideals, or even an uncountable collection of ideals. You'll still get an ideal. And the proof is basically the same thing that we did before, I'm pretty sure. Let's see here. Certainly, we know that arbitrary intersections of subgroups are subgroups, so that's good. And then if you multiply anything on the left or on the right in here, then you just use the fact that that anything in this intersection is in each individual AI. And so then R times that thing will be an AI. And since that holds for every I, it will be in the intersection. So you'll be good. One thing to observe here is that if you take the product, like if we consider this product like here, then if you take a finite product like A1 times A2 times A3, and those look like this, that will be in the that will be contained in the intersection here. Is that how that works? Right. And the reason that that works is because if you consider finite sums of things that look like A1 times A2 times A3 times all the way up through AN, where each AI is in fancy AI, then when you product those things together, because each one is an ideal, like for each AI, fancy AI is an ideal, and so you're taking this element AI and multiplying it on the left and on the right by a whole bunch of other elements of R, and so what you get is going to land in fancy AI, and that will hold for every single I, and thus this will be contained in the intersection. All right, and then lastly, if we go back to here where we have addition and multiplication, you can sort of see that if you take something and add the 0 ideal, then you'll just get back what you had. And then if you take something and multiply it by the entire ring, then it's going to be sums of the form AI times R, but that's just going to be equal to the ideal. And so it turns out that if you consider the set of ideals under addition with identity 0 and ideals under multiplication with R, these are monoids, and in fact they're commutative monoids, because you can see if you were to flip AB, well, certainly this is commutative since addition is commutative. For this one, if you were to look at BA, for some reason it's not quite so obvious to me that this one will be commutative. But certainly if our ring is commutative, it will be commutative. But other than that, so I'm not 100% sure on that. But anyways, it's not super important. It's just something to sort of look at it, and it's sort of neat. But other than that, it's not something that is really useful at all when you're doing exercises. So let's go on and do some more definitions. Again, this is more, we're still like warming up and still getting introduced to this topic, so there's a lot of definitions that we have to go through. All right, so if we have a subset X in R, so this is just any set, there's no structure on it. We can consider this set the set of all finite sums of the form R times xi, where xi is in X. So we take a finite number of elements x1 through xn from X, and we consider all things which are, we take these finite sums and we multiply them on the left by R. Then this is going to be the left ideal, which is generated by X. And we call it left ideal because here we're multiplying R on the left. Oh, and by the way, there we don't fix x1 through xn in this definition. Here this could be, you take any finite subset of X and consider this sum, and then you sort of consider all things of that form for every single finite subset here. But anyways, so you have this thing, and then you can do the same thing, but instead of multiplying on the left, you multiply on the right. And of course, this should be I equals 1 to n, and of course the xi's are all in X, but I didn't want to write all that out. Yeah, and then of course this is the right ideal generated by X. We don't really use those two very much. What we really use a lot is this. And this is the finite sums of the form R times xi times R. This is the ideal generated by X. So this is basically the smallest ideal. I think you can actually prove this, that this is the intersection of all ideals containing X. That certainly is what you do for the group theory case. You prove that the group generated by a set is the intersection of all groups containing that set. I think the same thing holds here, but I don't quite remember. And if it is true, we don't prove it here. But yeah, so it's basically you do like the least amount of work in order to take this set X and make it into a ring. Like you have to be able to multiply on the left by any element of R, you have to be able to multiply on the right by any element of R, and you need to be able to take finite sums. And that's exactly what this is. All right, and so this is the ideal generated by X. And we say that an ideal A is finitely generated if there is a finite collection of elements in A such that we can write A as the ring, or A as the ideal generated by A1 through AN. So this will be all finite sums of the form, or like finite sums of the form, like you take an element of R times an AI times an element of R, and then you just sum those up for all of the AIs. All right, and if it turns out that there is one element such that A is the ideal generated by this single element, so this will be like, you can think R1, A, R2, where R1 and R2 are in R, then we say that A is a principal ideal. And I think this is like, I'm not 100% sure why we use principal with a PAL at the end instead of principal like with a PLE. But I think it's because like a principal refers to like a person, like a school principal. And here we have like and of course the school principal is like important. And here we have just one element by itself, and that element is important. So maybe that's why we call it that, I don't know. But anyways, we say that R is a principal ideal domain, but we'll just call it a PID because no one has time to write out principal ideal domain. So R is a PID if every ideal is principal. Oh, and it's a domain. That's also important. Well, actually, I guess I shouldn't say that. What do we say here? No, in my notes we don't go into PIDs. We talk about PERs. So R is a principal ideal ring if all ideals are principal. And it turns out principal ideal rings, which are domains, end up being really important, and there's a lot of neat stuff you can say about them. And so principal ideal domains come up a lot, and so that's I see PID used a lot more frequently than PIR because I think there's a lot more interesting things you can prove about PIDs. All right, more definitions. So we talked about this homomorphism, this ring homomorphism, that we always get. It goes from Z to R, and you take M2, just taking the multiplicative identity in R and adding it to itself M times. Of course, 0 goes to 0, and then negative numbers means you just take the negative R and add it to itself however many times. So we know that the kernel of this is an ideal, and it's an ideal of Z, or the integers. So there is an integer n, because we know that all ideals in the integer, every ideal in the ring of integers, is generated by a single element n, and that's why we wrote this last time like this. It's because it coincides with this notation up here. But anyways, so there is some integer such that the kernel is the ideal generated by this integer. And we call this integer the characteristic of the ring R. And we'll just write char R. All right, so basically, let's see here. I guess, I don't know, when I was looking through the notes, in my notes I have it as written this way to define the characteristic subring. I think this is more wordy than we need. I think that what you can say is that the characteristic subring of R is just the image of the integers under this map. And so the way I have it in my notes is that if n equals 0, then the characteristic subring is just the image of the entire ring. And so what we see here is that if n equals 0, then what does that mean? Then the kernel is 0, so then this map is injective. And so the subring that we get, the characteristic subring that we get here, will be isomorphic to Z. But it'll be a subring of R. Now, if n is not 0, if n is greater than 0, then we know by the fundamental theorem of ring homomorphisms that there exists a unique ring homomorphism that goes from Z mod its kernel, and here modding out by the kernel, which is the ideal generated by n, which is, you can write it as nz, it's literally just Z mod nz. We have an injective map from here to R such that the map phi is precisely phi bar composed with the projection pi from Z into n, from Z into, this is the projection from Z into Z mod nz. All right, and what we do here is we define the characteristic subring to be the image of Z mod NZ under this injective map phi bar. And so there's really, well, because the image under phi bar of Z mod NZ is going to be precisely the image under phi of Z by this equation, and so there's no reason that we had to write this out separately. However, I think now that I think about it, I think the reason that we did this was to emphasize that here we have phi bar as an injective map from Z mod NZ into R. And so what's going to happen is that the image is going to be isomorphic to Z mod NZ. And so I guess that's the main thing that comes up with the characteristic subring, is that if n is 0, then the characteristic subring is infinite, or countable. Well, yeah, countably infinite. And if the characteristic is greater than 0, then the characteristic subring will be finite, right? Because it will be the image of a finite set under an injective map. All right, and so we have another fact that's associated with this. If R is a domain, then either the characteristic will be 0 or prime. And this, we're not going to write out proof of it, but it sort of makes sense because, okay, so it could be 0, but what if it's not 0? So the reason that this should make sense is that if you have a domain, then if you multiply two elements together, if you multiply together two non-zero elements, you won't get 0. And if you look at an ideal so if the characteristic of R is greater than 0, then we know that the kernel of this map is the ideal generated by n. And so what you get is you get a finite, the characteristic subring of R will be a finite subring which is isomorphic to Z mod NZ. And we know that Z mod NZ, if n is prime, then Z mod NZ will be a field. I don't know if we've proven that yet, but it's a pretty standard fact that if Z mod NZ is a field if n is not equal to p, but if n is prime, then Z mod NZ is a field. But if n is not prime, then you could take two divisors of n, which are not 0, and multiply together to get n, and therefore these would be two elements of Z mod NZ, two non-zero elements of Z mod NZ, which multiply together to give you 0. And so Z mod NZ is not a domain if Z mod NZ is not a domain if n is not prime. And so that's sort of what's going on in the background here, and that's what's motivating this. And of course, you could write out all the details for this proof, but I'll leave that to you if you want to. Another thing to observe, if we're just considering ideals in the integers, then the ideal generated by n, and you add the ideal generated by m, then what you get is you get the ideal generated by the greatest common divisor. Because what you can do is, basically you can use what can you do? Because these are ideals in the integers, you can take integer combinations of these and arrive at the greatest common divisor. And then once you have the greatest common divisor, you can get the entire ideal generated by that. If you look at the intersection of two ideals, then that will be generated by the least common multiple of m and n. If you have an ideal n which is contained in an ideal m, then that's equivalent to saying that m divides n. And that sort of makes sense because if n is an ideal which contains m, then right, n needs to be some, like you need to be able to take n and multiply it by some, or you need to be able to take m and multiply it by some number to get n. It's sort of something that it's good for you to like work out the logic in your head at some point. Here certainly it's easy to mix up like which inclusion corresponds to dividing. But yeah, you can work that out. And finally, if you multiply two ideals together, you get the ideal generated by the product. And those are just things that are, it's good to be familiar with these things, especially if you are doing exercises that are related to ideals of the integers, because these things will be useful. And yeah, that's all I have to say about characteristic rings and stuff for now. So from here we'll do, I think, the Chinese remainder theorem. So that's coming up next.